So my name is Andrea, and today with Matt, as Paul said, we are going to talk to you about LLVM-mca. So this presentation is mainly structured in three parts. In the first part, I will talk to you about this new tool, LLVM tool, and what is it exactly, how to use it, and to generate performance reports. In the second part of this presentation, Matt will be talking to you about the internal design of MCA. Then there is one last slide about future work, so to-do work on MCA. So LLVM-mca, okay. Oh, sorry about that. Yep. Okay. Okay. So MCA stands for Machine Code Analyzer. It is a static performance analysis tool. It takes as input a block of assembly code, and the tool will run a simulation of this block of code for a number of iterations, and at the end of this simulation, which is for a specific target processor, it generates a performance report. And most part of this performance report has been inspired by the report generated by another tool, which is the Intel Architecture Code Analyzer. So people who know about this other tool will find a lot of similarities. The major difference between LLVM-mca and tools like the Intel Code Analyzer or any other tool which is out there that does a similar job is that MCA only uses information directly available in LLVM in the form of machine scheduling models. Okay, I don't know why it doesn't work. Okay. So what are the use cases here? MCA can be used, for example, to predict the performance of a block of code. And let's say we have multiple blocks of code that potentially do the same thing, but we want to see which one performs best for our target processor. So MCA can be used to generate a report for each one of them, and then we can compare the various reports to see which one is better in general. But because the report generated by MCA is quite verbose, it can help identify potential performance bottlenecks. So to help answer to the question, why is my code slow, for example. And last but not least, MCA can be used as a good way to test machine scheduling models, or even find some silly mistakes sometimes in, let's say, the number of cycles associated to instructions or number of opcodes and so on. So I'll start with a simple example. On x86, this code is AVX. It's a dot product. We have a vector multiply followed by a horizontal reduction implemented by doing 2 steps of horizontal adds. Here, vectors are XMM vectors, so 128 bits. In particular, each vector has 4 elements here. And the notation is the format is AT&T, so the destination register is the last operand in the sequence of each of these instructions. What we have is that if we try, let's say, to analyze the performance of this code on a x86 AMD Jaguar processor, for example, we can see with perf that the throughput tends to 1.5 instructions per cycle. Now, just to give you a bit of background on this particular target processor, we have that the floating point unit is dual issue, so we have the scheduler serving 2 pipelines, which in these slides are JFPU0 and JFPU1. So how can we do a similar analysis with MCA and maybe get even more details about this run? We pass the assembling input to the tool. We have to specify the processor. Here is option MCPU. Bitiver2 is the code name for Jaguar. We can optionally pass a number of iterations. It's not mandatory. By default, it will be 100 iterations. But the idea here is that we want to reach a kind of a steady state where to compute all of the throughput numbers. So in this particular example, it was 1,500 was a good number, but it's not too significant. And the report is quite verbose, so bear with me. This slide shows some of the information generated by MCA. So we can start by looking at the lower half of this slide, where a bunch of information about instructions is presented in the form of number of micro opcodes, latency, and reciprocal throughput. Now, all of this information is not encoded in MCA, is is directly queried on the machine scheduling models in LLVM. What is interesting about this part of the report is this block of numbers here. These are all throughput indicators. We have the observed number of instructions per cycle, the IPC field over there, number of opcodes per cycle, which in this case coincides with the instructions per cycle, basically because each instruction decodes to a single complex operation on this platform. And we have the dispatch width. This quantity is directly coming from the machine scheduling model. It says how many opcodes per cycle can be dispatched on this target. And so that is an upper bound on the size of a dispatch group. And then we have another quantity, which here is called block reciprocal throughput. It's essentially like a number of cycles per block, where block is the input that we provided to MCA. In this case, we define it as a theoretical minimum number of cycles. And the reason why it's a theoretical minimum is because when we compute this quantity, we don't take into account data dependencies. So the only thing that we account for in this formula are the dispatch width, the availability of hardware resources on the target CPU, and what resources are effectively consumed by instructions. But why this quantity is important? It is important because if, let's say, we divide the number of opcodes of this block of code by that quantity, we get another quantity, which in this case is a theoretical minimum number of opcodes per cycle. And any delta between the dispatch width and that number means we cannot do any better regardless of the data dependencies. There must be a problem because either we are doing a poor usage of hardware resources or there is too much resource pressure. So we can have a look at another part of the report generated by MCA to have a better understanding on where the resource pressure is. So in this case, we have resources named according to the naming convention in the machine scheduling models. We have tables where in the horizontal axis we have resources, vertical axis we have so-called resource cycles. And we have these cycles are effectively cycles consumed by instructions. For example, if we refer to the last table down there, on average, on every specific resource. And then we have a the cumulative numbers in the first table. So the reason why this is important is because essentially what this table is telling us is that we spend twice as much time on floating point pipeline 0, the JFPU 0, than on floating point pipeline 1. And that is because the horizontal HUD requires the float header, which is available only through floating point pipeline 0. But this is a potential problem because ideally we would like to have those numbers all uniformly distributed among all of those resources. So let's say rather than 2 and 1, 2 and 1, we would like to have 1.5 on each one of them. And the reason why this can be problematic is because if we ask MCA to generate more details about this run, let's say by specifying this flag, which is called -scheduler-stats, we can see how, according to MCA, we had that the floating point queue was often full for the entire simulation. And that is because there is an imbalance between the dispatch width and what effectively is the issue rate on this floating point unit. So we were only able essentially to issue 2 opcodes half of the time, but the dispatch logic will still try to dispatch as many opcodes as possible every cycle. So this sort of imbalance puts a lot of pressure on the buffer, which, as we can see in the lower half of this slide, it was almost always full, 18 entries. And these may cause pressure on the upstream dispatch logic to the point where the dispatch logic cannot always effectively dispatch a full group of 2 opcodes. And we have in this last view that half of the time we were only able to dispatch a group of 1 opcode, and the reason was the scheduler queue was full. There is one last view which I think is interesting mostly for debugging machine scheduling models, but it also gives an idea about how the tool sees instructions executed over time. And here we have this view called timeline view, where in the horizontal axis we have cycles starting from relative cycle 0, and vertical axis we have instructions contributed by the various iterations. Every single element in this table represents a state in the execution of an instruction. So we go from capital D, which stands for instruction dispatched, to capital R, which is instruction retired. So we can see how the tool sees instructions executed. And this is also good for debugging scheduling models, because we can see almost immediately whether, okay, some instructions have a strangely long latency and they shouldn't, for example. But what is interesting is that at the end of this view, we also print another table which is called average wait times. And the reason why this table is important is because it shows the number of cycles on average spent by instructions on in a scheduler queue while waiting on the operands or not. So in this case, the first horizontal HUD, for example, spends twice cycles when the input operands were already available, but the pipeline was not available. And this is an indicator of potential bottleneck caused by resource pressure. So this is all for my part, and now Matt will talk to you about the internals of MCA.
All right, so the next part of this presentation is about some of the design decisions of MCA and the architecture behind it. So back in March, Andrea made the first commit of MCA into the tools directory of LLVM. And at that time, it was a very monolithic framework. Since March, we've been working to make it a much more modular framework. And this will allow users to make use of MCA to explore their own scheduling models or to explore their own instruction pipeline simulations. So going back to that modularity bit there, we've got three main components that make up the internals of MCA. We've got the pipeline, which is just a container of stages. The stages model the processing logic of the simulated instruction pipeline. And they follow a push model. So stages take as input an instruction, and they do some processing to that instruction, and then they push that instruction to the next stage. And then lastly, we have the hardware units. The hardware units are used by stages, and they simulate things like the register file or the scheduler. Here's a visual depiction of what I just said. You can see the pipeline has got stages, and here I've outlined the 4 stages that make up what we call the default pipeline. This is what MCA has just right out of the box. And we've got a fetch stage. Now that is not simulating the actual hardware fetch, it's merely just producing instructions. It's not the front end. So it fetches instructions, it takes those instructions that were defined by the user and passes them to the next stage, which is dispatch. Dispatch interacts with the register file and the retire control unit, as well as querying the next stage, the execute stage, saying, hey, is there availability to schedule this instruction? And if so, it gets scheduled. During the execution stage, the execution stage will communicate with the scheduler and see if there's what the next instruction is to execute. And lastly, we have the retire stage. Retire stage is responsible for reclaiming any resources that were required during the execution of that instruction. Now, I've highlighted here a few interesting bits. The top 2 pieces there, the register file and retire control unit, those can all be described via table descriptions and table gen. The bottom 2 bits there, the scheduler and load store unit, those are highly customizable pieces. And they have functions like, for instance, the scheduler has a function that you can override to change the scheduling policy. So that will allow you to explore your own scheduling models. And the load store unit has a similar function you can override to model different memory consistency policies. So here's the source code of our default pipeline. Now it's going to look like a very verbose screen, but all I want to show is just the composability of this. So you see here we've defined all the hardware units. The next part is to define your stages, which make use of those hardware units we just defined. And then lastly, we have to just string everything together. So this is just specifying the order of the stages. And the last bit of our modular framework is our event framework. And this follows a publish-subscribe model. And the listeners, they will subscribe to stages, and the stages will produce events, and they will publish those events. So anything that is listening for events will then get those events. So those output reports that Andrea just presented, those were all basically what we call views or event listeners. They were collecting events during the simulation and producing various reports from that information that they collected. And lastly, we've got event types. And if you create your own stages, you can create your own event types, but these are what MCA has just by default. And I've just kind of tacked this back onto the bottom of that original description that I showed just a minute ago. So now I want to walk through the execution of a single instruction through MCA, just to show you what MCA is doing internally. So this is the same example that Andrea just presented. That's the block of 3 instructions that are the dot product. So you can see here in cycle 0, you'll notice that there are 2 capital Ds there in that middle box. And that just means that because we are simulating a Jaguar CPU, which has a dispatch width of 2, we were able to dispatch those first 2 instructions in the example. So the multiply and the horizontal add. We've also highlighted in bright red the dependency. So the output of the first instruction is required as input to the second instruction. And the blue boxes in the model are just describing the hardware components. Okay, so now in cycle 1, we are now able to execute the first cycle of the multiply instruction. And because there's now availability, we're able to dispatch that last instruction. So you see the capital D at the bottom row there, and the little lowercase e represents that execution for that first instruction. And the equals is just saying that we can't begin executing that second instruction just yet. We've dispatched it, but we can't execute it. All right. For cycle 2, we are now able to execute the second cycle of that first multiply instruction there. And again, the other 2 instructions are still just waiting. In cycle 3, we have now completed execution, hence the capital E. And we can now start executing that first horizontal add there, which is the lowercase e. And then lastly, we are able to retire that first instruction. So there's a capital R there that just signifies that we're able to retire it. And the second instruction, the horizontal add, is now able to execute its second cycle. Okay, and the last part of my talk here is going to be about going back to that modularity piece that I started off with. So we want to expose MCA to other tools. And the way we have it designed right now, MCA exists as 2 pieces. We've got the driver, and then we've got the actual library components. The pipeline, the stages, the hardware units, those all make up the library. Eventually, we'd like to move these core MCA abstractions into the core of LLVM so that other optimization passes or analysis passes can make use of MCA abstractions. So with that said, I'm going to pass the mic over to Andrea here, and he will conclude with the future work.
Okay. So there is one last slide about future work on MCA. I will quickly go through these 4 points. So first of all, as you've seen, currently MCA generates quite a verbose report, but it would be nice if the tool were able to generate a very quick feedback in the form of the code suffers for bottlenecks, and this bottleneck, let's say, is caused by data dependencies or resource pressure. So we would like to add so-called bottleneck hints to the tool, so that people can get a very quick feedback immediately, and they don't have to find these things by themselves by just browsing all of the lengthy report generated. And then there is another bit of work where Matt is working on this, and this is the adding binary support to MCA. At the moment, as you saw from the initial example, the code is passed in input as an assembly block of code. But we would like to add support for binaries too. And that poses a lot of questions, such as, okay, how do we identify the blocks of codes that we want to have analyzed by MCA, and so on. And Matt has a prototype for this. He will be sending it upstream after the conference, along with an RFC. And obviously, we want to improve the simulation of hardware resources, and as you can imagine, the quality of the analysis is heavily dependent on the quality of the scheduling models. So there is an ongoing effort put into improving the existing machine scheduling models. In particular, I mean, speaking for ourselves, we will try to do our best to improve those on x86. And I think this is all. So thank you.
Great, thanks guys. We have microphones set up in the middle here, or if, and just go ahead. And if there's somebody off to the side, I can try to run the mic, this handheld mic over to you. Go ahead.
So I had two questions. The first one was how easy or difficult you all think this would be to extend to a VLIW architecture, where there's a notion of packets and multiple instructions in a packet. So your dispatch phase would basically dispatch a packet, but then your actual going out to the instruction units would be the instructions inside the packet. Right. So that was the first question. And then the second question I had was whether y'all are considering extending this to a cache model down the road, right? Not just looking at the scheduling units, and so not just looking at the units, but also going further into maybe with the help of PGO or something, bringing a cache model into the picture.
Okay. So currently we only have the default pipeline, which is making a lot of assumptions on what will be the execution, specifically in the hardware backend. So it may be that some of these stages will not be enough to describe a VLIW, and that will require customizing that pipeline. So ideally, we have been thinking about this problem, and there is obviously, we cannot obviously provide a default pipeline which is good for every possible processor. So the whole idea of having it modular is so that people can specify their own custom stages. And ideally, it would be nice if sub-targets in LLVM could specify, let's say, via table gen, what is the composition of the pipeline that they would want to use when simulating on MCA and execution. About caches, at the moment, we always assume optimistically a load-to-use latency, which is the one specified by the vendor and often matches the L1, the latency from the L1, the load-to-use latency from the L1. But we could complicate that model, but currently the load store unit simulated by MCA is very simple, and it doesn't have the concept of caches. It doesn't have the concept of store-to-load forwarding, for example. It doesn't try to do any sort of aliasing, alias analysis on stores and loads to see, for example, if we can do any better in terms of anticipating some loads or things like that. But that can be, it's all written in a way that it can be extended, so people can override, can create their own derived class for the load store unit and expand it. But at the moment, it's not there.
Any more questions?
Hi. So in the beginning, you showed you running for a number of cycles. So I wonder why is that? Are you simulating randomness or?
So by default, users don't need to specify the number of iterations. So you are talking about the iterations flag, yeah. It's just because we want to reach a steady state where we compute all of the throughput numbers. They tend to stabilize over a certain number of iterations. So normally we see that 100 is a good default, but in this particular case, it was nice to use 1500 because all of the numbers were nicely converging to this 1.5, which was matching the output from perf. In reality, we don't make assumptions on when we have reached a steady state. So the user have to provide that number if it's not happy with that 100.
One more question.
So thanks for the great talk, and I have somewhat a researchy question. And so, if I understand correctly, you want to have all the inputs available, and the program should be runnable for you to do this measurement. Is there a possibility that I can run code where the inputs is not known, and I have loops, but I somehow kind of approximate it? So.
Sure. So the code we showed right there, you can specify your target. So if you want to simulate this on a different target, you can just pass the -mArch or -mCPU flags. And we were just analyzing just subsets of blocks of code. So those 3 instructions that we showed in our example, that's exactly what we were just analyzing.
So you do handle pieces of code where you don't have the values for all the variables that come in?
The tool doesn't make any assumptions on what will be the value in each register. The tool doesn't know also anything about control flow.
Right.
But also a branch instruction is just only analyzed for the purpose of latency and throughput, but effectively it doesn't affect internally the state of a instruction pointer, for example. And so it's all about a single basic block, let's say. Mm-hmm. Okay. It could be the innermost, it could be like a block of code from your innermost loop that you know to be hot and you want to have analyzed by the tool, for example. That's just...
Okay.
So,
okay, thank you.
Yeah, there are indeed limitations.
Yes, so we're over time, I'm sorry, but Andrea and Matt will be around if you want to talk to them later.
Answer to the questions.
So if anybody wants to leave to go to another session, now is the time to do that.
Thank you.